it works.
Okay, I guess everyone already knows Professor Tom Kurtz. He doesn't put his name on the slides.
No pictures, no video, no names. So this will give you an opportunity to relax before coffee. I've noticed a pattern over in recent years that since people know I ordinarily run over my time by a lot, they schedule me before the coffee break because they know by that point I will be desperate for the cup of coffee and therefore I may finish in time. Let me get rid of the echo here. Now, when I got the invitation to come to this conference, and I saw, what is it that I might know that might at least be of some passing interest to the group here? So I wrote to Ruth and Jeremy, and I saw the word control in the title. And I thought, I know a little bit about stochastic control. So I wrote to Ruth and Jeremy, and I said, can you give me a few references of papers that you think might be relevant? And they sent me some papers, and I looked at them, and I'll mention a couple of these by the end of the talk. Now, the other thing I think most of you who've have known me for a while know I am a mathematician. I am motivated by big general theorems. Now, if anything that sets me apart slightly from some other mathematicians is that I try to make sure that my big general theorems actually cover the examples that real people care about. Okay? So here's what you're getting today. I'm going to describe a big general theorem. Okay? And then I'm going to explain why this big general theorem doesn't cover the examples you probably care about. All right? Now that's not necessarily a bad thing, because that means there's work to be done at the end of this. So if you find something interesting here, you may also find some problems to work on. All right, specifying Markov chains. Most of you, I think, would have encountered much of this stuff, but there's a little book that David and I wrote a while back that explains a lot of these things in the context of the continuous time Markov chain models that some of you were interested in. And I don't mind promoting this book because they paid us up front, so we're not earning any royalties off of it. Okay, so continuous time Markov chain, we'll keep it simple. You think of this as X as being the vector of numbers of chemical species, and these processes evolve by jumps, and there's some subset of possible jumps. These are the reaction vectors in the context of chemical networks. So if I know what the possible jumps are, and I count the number of jumps of each kind, so if I have m different chemical reactions, and RL simply counts the number of times that the nth reaction has gone forward, then you have a simple identity. If you know where you start, and you know how many jumps you have had of each type up to time t, you take x of 0, you add on these perturbations, and you get what the state of the process at time t. Now the cool thing about these RLs of t is you know that we determine the jump rates for these different possible jumps by the propensity or intensity, depending on what world you live in, and for this crowd, I suppose the propensity of each reaction. You know that the probability of seeing a jump in a little interval of time is going to be proportional to delta t times whatever this propensity happens to be. And what that immediately suggests, and again, take a look at the book, what that immediately suggests is that I should be able to write the counting process RL of t as a time change of a unit Poisson process. And that leads to a very useful kind of stochastic equation that your continuous time Markov chain should satisfy. All right, so this is one way of specifying the Markov chain that corresponds to these transition intensities. Now, let me, patience now. I'm going to scare you all, or a lot of you, in a half a second here. The generator that goes with one of these Markov chains is an operator that looks like this. This is the intensity. This is the rate of seeing a jump in the Markov chain of size or of type zeta L. All right, so if I take this collection of functions, f, and I'm going to take my collection of functions simply to be, we're going to be working on a countable state space, so this collection of functions f is just those functions for which f of x is equal to 0, except for some finite collection of points x. All right, those are going to be the functions that I care about. And if I take this function f of x of t, I claim I can write the left-hand side in terms of these RLs where I have centered, I've taken the RL and I've subtracted off the lambda L. And what that makes the RL tilde makes it a martingale. Do not panic. You don't need to know anything about martingales. All right? But what that means is this expression is a martingale. And the only thing you need to know about martingales of this type, see at time t equals 0, this is 0. The only thing that you need to know about martingales is the expectation of this quantity is 0 for all t. Okay, it starts at 0. If it's a martingale, its expectation is going to be 0 for all t. All right? Now, I claim you already know that. Because here's my martingale, and there's this notion of a martingale problem, and martingale problems are useful in characterizing the process that goes with these operators. Much for those of you who have broader stochastic Markov process interests, most of what I say today actually extends to a very large collection of Markov processes, controlled Markov processes. Okay, so this is a martingale. I claim that this expectation of this thing has to be 0, and I claim you already know that. Okay, so if the expectation of this is 0, of this quantity is 0, then if I rearrange terms, I see that the expectation of f of x of t has to be the expectation of f of x of 0 plus this interval. Well, let's look at a particular choice of what f of x is. It's just be the indicator is the function that's 1 at the point y and 0 everywhere else. If you plug this function into this identity, lo and behold, you get this. And if you close one eye and stare about that for a minute, you'll see that what this identity says is that this probability satisfies a certain differential equation. And all of you who do stochastic models and chemical networks know that this is just the master equation or the forward equation and so on. So all I'm saying, give me my martingale. I love martingales. I once had a couple of students that called me Mr. Martingale. But again, what you need to know about martingales is that martingales have expectation 0, and for these particular martingales, you already knew that before I started wasting your time this afternoon. Okay, that's standard continuous time Markov chain theory. Continuous time Markov chains are solutions of these martingale problems, okay, which is related to the forward or master equation that you already know. All right? Now, some equivalence. Remember, I wrote down a stochastic equation. I've told you that there's this idea of a Martingale problem, and you already know the master equation. All right? Equivalence. The solution of the stochastic equation is a solution of the Martingale problem, provided one thing. Those counting processes may blow up in a finite amount of time. Okay? If they do, let's just define the solution of that equation to be infinity. And let's assume that f infinity is equal to 0. Okay? Then every solution of the stochastic equation is in fact a solution of the corresponding Martingale problem. Every solution of the Martingale problem gives you, by taking these expectations, gives you a solution of the master equation. All right? The converse also holds. Every solution of the forward equation or the master equation corresponds to a solution of the Martingale problem. Every solution of the Martingale problem stopped the first time one of these counting processes hits infinity is in fact a solution of the stochastic equation. So there are these more or less equivalent ways of describing our process. Now, we have control in the title, so let's go on to the control. All right, well, that's easy if we start with the stochastic equation. Okay, I have my process x. This looks exactly like the stochastic equation we had before, except I want to control my process in some way. So I have some space, I don't care what it is, can be countable if you like. And I have these, I'm going to have a control process that goes into that takes values in the state, and my transition intensities will now be a function both of the state of the process and the control that I'm using. Okay? Same sort of argument, that's kind of easy, right? You can think of, well, those of you who do controlled ODEs, this is exactly what you would get. You get your ODE, and if you want a controlled ODE, you use the controls and the coefficients of your ODE. So it's exactly the same sort of thing.
So the functional dependence on the state is arbitrary here?
Yeah, well, pretty much, as long as lambda L is some positive, is a positive function of the state and the control. Okay? I mean, if you want to think in terms of chemical networks, that's sort of where we're going. Okay? Okay, so we got the stochastic equation. Corresponding to the stochastic equation, I can write the control generator I did write it down. Just as we did before, the only thing is now we have this control appearing here. This object needs to be a Martingale. Okay, so that's going to be the basic structure that for defining the stochastic processes that I'm interested in, is that all of these objects will be Martingales, but I already told you you don't need to know anything more about these Martingales other than their expectation is 0. So let's take the expectation, and what do we get? We get an identity of just like we had before, okay? The expectation of f of x of t, blah, 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 okay? If I let the expectation of x of t, so nu t is the probability distribution of x of t, so I can write this expectation as the integral of f of x against nu t. What's new here is I have both a state and a control. This expectation is I can write that as an integral against some distribution over the state space and the control space, and we'll just call that mu. This is equal to 0 in terms of my probability distribution for the x process. This identity becomes nu t integrated against f is equal to nu 0 integrated against f plus af, which is now, af now is a function of two variables, integrated against this mu t. So for any solution of my controlled Martingale problem will satisfy this identity, okay? And as we had before, there is almost a theorem which says that if mu t and if nu t and mu t satisfy this identity, satisfy this equation, then there exists a stochastic process, a controlled stochastic process that will be a solution of my Martingale problem and will be a solution of my stochastic equation modulo this problem of one of those counting processes blowing up. All right? Fair enough. So what can we do with this? Well, when I said this is almost but not quite true, that any pair of valued process or functions, any pair of measure valued functions that satisfy this identity for every f, this has to hold for every f in, again, my domain are functions f that are non-zero only at a finite many points. This, again, is basically the master equation. You can think of it as being a controlled master equation. And this converse statement that every solution of this controlled master equation actually corresponds to an honest-to-goodness stochastic process, it's almost but not quite true. And what goes slightly differently is what's a martingale is an object that looks like this. By measure mu, this is a probability distribution on the state space plus the control space. I can always write that. This is the one-dimensional, this is the distribution of the x. I can always write this distribution on the product space as this is essentially a transition function. That's a terminology you probably know. Integrated against the new dx. So the thing that's a martingale is this object here, okay, where I have to do this integral against this transition function. Okay? So we have this deterministic equation for my two measures, my one-dimensional distribution nu and my joint distribution on the state space cost the control space. This equation here essentially determines my control process just as the ordinary master equation essentially determines your continuous time Markov chain.
Sorry, what is the assumption on U of t in all this? I mean, first of all, it has to be conditionally independent of the future x and so forth.
Yeah, but
what are you assuming?
the nice thing about the martingale, that sort of gets forced by the fact that these things are martingales. Notice that when I wrote the stochastic equation, one thing, this is your comment here, is these stochastic equations are essentially a simple way of writing down what many of you know as what's the next reaction method, right? This is just a way of writing down the next reaction method. Now, if I'm going to control this process, it's cheating. No, in the next reaction method, what you know is the next time each of these, you're assuming you know the next time each of these y's jump. You can't use that information in the control. That would be cheating. Okay, that's what Eduardo is concerned about. But the fact that these things are martingales essentially takes care of that problem. If these things are all martingales, then you can't have that. You can't be exploiting too much information about the future of the process. Okay. So where do we go from here? Well, if you're into any kind of control, you frequently are looking for some kind of optimal control. And I'm going to talk about cost minimization problems, long-run average cost minimization problems, partly because the theory that goes with these things is significantly less complicated than the theory that goes with other kinds of cost structures. We'll come back to that briefly later, assuming I don't get kicked off the stage here. I'm not sure when I started or when I'm going to end. But at any rate, okay. So we're interested in the long-run average cost, okay, which, if everything is nice, this limit should be the integral against c of x and u and some probability distribution over x and u. The Martingale structure, or the expectation structure of this thing, when I divide this expression by t, well, my functions that I'm working with are bounded. So if I'm dividing by t and letting t go to infinity, this term is going to go away, this term is going to go away, and the long-run average should better be something that looks like this. Okay? So what does this structure give us? Well, it gives us a linear programming problem. If I want to solve this optimal control problem, you see, these are costs. I want to minimize this asymptotic long average asymptotic cost, which means I want to find the pi that minimizes this expression subject to the constraints, okay, that these integrals are all zero. Now these are linear functions of pi. So this is a linear programming problem. And in fact, in the case of finite Markov chains, Manne actually posed this kind of linear programming problem for finite Markov chains a long time ago, because in the case of finite Markov chains, it's just a classical linear programming problem. There isn't anything new or subtle about it. In the cases that we may be interested in, our Markov chain may have a countable state space, so it's slightly more general. Okay? But all this machinery works for much more general Markov processes. Works for diffusions and a lot of other very general classes of Markov processes. So we've got a linear programming problem, all right? And, you know, assuming the minimizing pi exists, okay, there is a theorem that says if I have a pi that achieves this minimum, it annihilates the AF and achieves the minimum of the cost function, then my claim is there is, in fact, a solution to the Martingale problem. A solution to the Martingale problem gives us a solution of the stochastic equation, at least until one of those counting processes blows up. All right? So solving this linear programming problem really is solving a stochastic control problem. Okay. We need some conditions to actually be able to say with certainty that this minimizing pi exists. Okay? And I'll warn you right now, I meant to write this on a slide. And whoop, I went the wrong direction. In this paper, there is an incredibly stupid error. There's also a published correction. Okay? Because there is a critical hypothesis in the proof of the existence of a minimizing solution. And that is the hypothesis that for some reason didn't appear in the paper, although one knew very well that it was needed, was that if we have a bound on all of these AFs, which is some constant depending upon F plus another constant depending upon F, times the cost function, but raised to some power beta which is less than 1. Okay? With this condition, you have all of the, if you know what I mean by compactness, that you need, that as soon as you have one solution, of of this equation for which the cost is finite, then you know that there is a minimizing function for this one. And again, this is a very general theorem that applies to all kinds of different kinds of Markov processes, again, including diffusions and so on. Okay, this is my big general theorem, all right, as promised. But the other thing I said is I was going to tell you, one more interchange in here. I'm still going to tell you why this big general theorem probably doesn't cover the examples you're interested in. So when I went looking at papers, I looked at a couple of papers out of Khammash's group in Basel. And there they look at ways of sort of controlling chemical networks. And their control mechanism is based on a set of reactions of this form. Let me explain what this is. The Z's are molecules that are introduced, or what I think they would like to be able to introduce into their chemical network, which can be used to control certain behavior in the chemical network. Okay? Now, the original chemical network, my X1 and X2, they do this in more complicated settings. These are the molecules that I'm interested that are in some reaction network that I'm interested in controlling. Okay? Now, let's see what this, if I observe Z2.
Sorry, there is a reaction missing, right? X1 is supposed to be affecting X2. Isn't that reaction missing between X1 and X2?
I'm missing all of the reactions that involve
just
X1
one
and
X2.
X2.
I
mean, it could be more complicated. They do this for more complicated things. Note that if I'm observing Z2, since Z2s appear at a rate which is proportional to this molecule, the molecule's X2, number of X2s that are around, observing Z2 gives me information about X2. All right? And the point of this reaction here is that there's somewhat complicated interactions between Z1 and Z2 is this interaction between Z1 and Z2 creates new X1s in the network that I'm interested in controlling. So it's the X1s, this gives my controller information about X2, and this reaction, and of course the interaction between these reactions, has some effect on the original network that I'm interested in. Okay? Now, with that in mind, okay, here's why my big general theorem isn't probably very useful in this context, okay? Delays, okay? Andrew Murray made some comments about the problems of delays in these chemical networks, okay? My big general theorem tells you that you have that your control is dependent upon the current state of the network. Okay? Well, this assumes that as you control, you know the current state of the network, and you can use that current state to actually do your controlling. Well, if the information, as would be the case, the information, what did I do here? Sorry about that. I'll figure out what I want to do here in a second. You're getting information in this setup here, you're getting information about the network, but because you're only getting it through these additional reactions, you're not really getting information about the current state of the network. You're getting information about, after some delay. So that's the first problem. In the big general theorem and the structure that I've developed, the assumption is that you know the current state of the network that you can use then to define your control. Secondly, in this setup here, well, you're learning about X2, but who knows in this network that you're kind of trying to control, there are lots of other things going on. So you're only working with partial information about the reaction network that you care about. All right? So the big general theorem assumes that in general assumes that you know exactly what the current state of the thing that you're trying to control is. Okay. There has been, a fair amount of work done on controlling what would be called partially observed stochastic systems. So there is some work out there to get started, but I'm quite confident there's significantly more work to be done here. But there is a structure, this big general theorem, I'm relatively certain could be extended to work with partially observed systems. This problem, it may get a little bit complicated. This difficulty, I think, may be more easily addressed than the delay problem. At least if you're motivated, as I am, for big general theorems, because as soon as you start incorporating delays in your model, you get all kinds of things get very messy. Okay? The third problem is in some sense not a problem at all. I've defined this, the costs in terms of long run average costs. The Khammash papers that I mentioned also look at long run average, or look at essentially stationarity, not so much cost structure, but the stationarity. It occurred to me while I was listening to Andrew Murray yesterday, and he was talking about the process has evolved, but then they're inside a cell, but then the cell splits. Okay. So maybe it doesn't. It's not so true for synthetic biology, but if you're actually looking at processes inside these cells that are periodically going to split, using long-run average costs would probably not be as good as using some kind of cost structure that, say, is a function of the state of the cell or the state of the processes at the time the cell splits. Okay, that's not so much of a problem, although these first two problems I mentioned would still exist, because you can do the same kind of structure with a cost function that, say, would be a function of the state of the process at the time the cell splits. You get the same machinery with the same kind of general stuff, although you're still stuck with the first two problems. And I'll quit. Okay.
He wants the coffee.
Yes!
Oh, do we have questions?
So,
Everybody else?
this linearity, the coming back to a linear programming problem is key here. So which of those assumptions do you think is going to demolish this?
Well, again, the solution to your linear programming problem here gives you what's a relaxed control. It's like that's not so uncommon at all, even in deterministic theory. In fact, some of you may remember L.C. Young or don't L.C. Young, within months of being at Wisconsin, I was listening to Elsie Young talk about chattering controls, which are really these relaxed controls. Again, the problem for a lot, the sort of chemical network issues is, you probably don't know the whole state of the network you're interested in, so you can't really use the whole state. So you need to convert this to some kind of partially observed. So it becomes a combined control and filtering problem. Okay. And then, of course, the delay.
And the delay is another
The delays, I think, will drive you crazy.
So for relaxed controls, typically when in the deterministic optimal control problems, one can, it's not an issue because of weak star compactness. So when you have linearity in controls,
Yes. So I thought about that earlier. I should have put in.
So there's something similar in this case.
Yes.
Okay.
Yes. In fact,
okay.
If in setting up my control problem, the controls, the U's all appear essentially multiplicative.
Right. So if there were kinetic rates, for example,
yes,
then you would not need to.
Then when I get down here, I got my eta. But if these U's are multiplicative, then I just integrate them out.
Right. And what I'm saying is that basically is the case whenever you have, say, kinetic rates being, so if you have temperature control, we have some sort of kinetic rates, which we are the enzymes, then you don't need to talk about relaxed controls, I believe, unless.
Yes, exactly.
Okay.
Exactly. I really intended to put that in. Right.
Other questions?
Going once, going twice. All right, well, if I haven't intrigued any of you, I will still be around tomorrow.
Okay, let's go back. We'll come back at 4:30 with a colloquium.
So, in terms of the and actually I want to hear about this stuff with Eric. So, I mean, maybe I went to this.